topic for today is where I'm going to talk from is the Connexus SRS training class, and there's a section related to manual shutdowns. And manual shutdowns, honestly, is a topic where there's information in the standard that I'm going to explain where that information came from. Being on the standards committee, I'm going to explain to you how it's going to change in the next version of the standard. It's going to get even more watered down than the watered down it is now. And then I'm going to talk a little bit about what options you have when you're designing your safety instrumented system. Ultimately, I'll give you this key message to start out. What you need to do for manual shutdowns is whatever you wrote down in your SRS. But you need to really think about what belongs in your SRS. Manual shutdowns is discussed extensively inside the Connexus Process Safety Training Center, the Safety Requirements Specification page. So that's going to be section 10. In this lecture, we're going to talk about manual shutdowns. We're going to begin with a discussion of the standards requirements. We're going to talk about considerations of use of manual shutdown. So, do you actually need it? When do you need it? Why do you need it? And if you determine you need it, then the next bullet point is, what are my options for actually implementing a manual shutdown? There are a lot of different ways to do it. Some good, some bad, some more elaborate, some less elaborate. And then we'll go through the workflow for shutdown design. So manual shutdown design workflow. How would you specify it in a normal SIS design project? Let's begin at the beginning with the standard. So what does the standard, the 61511 standard, say about manual shutdown requirements? Clause 10.3, everybody knows what clause 10.3 is. It's that bullet point list of everything that needs to be included in your safety requirement specifications. That clause says that you need to document the requirements for manual shutdown for each SIF. So kind of unpacking that a little bit, what that clause is saying is that if you need a manual shutdown, you need to document that you need it, and you need to document how it's actually going to be implemented. And we'll show you how to do that when we get toward the end of the discussion. Now, in clause 11, you remember clause 11 is the detailed design clause of the standard. It states in 11.2.8, a requirement is manual means, e.g., emergency stop push button, independent of the logic solver, shall be provided to actuate the SIS final elements, period. No, not period. Unless otherwise directed by the SRS. So this actually, the way it's written right here, the way it's written right now in the current version of the standard is onerous, but it's not. What this clause is saying is that every SIS final element needs to have a way for you to de-energize it. Well, actually not even de-energize, actuate it. So if it's an energized to trip final element, you need a manual means to energize it in the event of some sort of catastrophe. So for some reason, the logic solver's not working, you need some way to move that valve. So a manual switch to activate a final element. Manual switch to activate a final element. You need to have it. You shall have it. Wow. Unless otherwise directed by the SRS. So what this clause is actually doing is it says that if your SRS doesn't say anything about manual means, it doesn't say anything about manual means, then you need to put one in for every final element. Furthermore, it needs to be independent of the logic solver. That is a really tough requirement for all of you that have remote control rooms. I mean, a lot of operating companies have spent millions, tens of millions, hundreds of millions of dollars to move your control rooms out of the plants to keep people safer. Um, and when you do that, if you want to be able to have a switch in the control room to manually de-energize a field element, we're talking about a lot of wire. That's a very expensive thing to do. And you need that for every valve? Ooh, sounds super, super expensive, sounds super onerous until you get to that last bit that says, unless otherwise directed by the SRS. So you, as the engineer in the SRS, can say, I don't want to have any shutdown valve, or I don't want to have any manual shutdowns. And there you go. So the design is whatever you want as long as you write it down. But if you don't write anything down, you need to have a switch that will activate every final element separate from the SIS logic solver. So basically, the SIS logic solver, your output card, is going to send voltage out to the field, and you need to interrupt the voltage with a switch somewhere between the logic solver and the final element in the field. My goodness, that sounds really expensive. Okay, so I'm going to stick here for a second because guess what, people? Everybody get comfortable? It's story time. I need to explain to you where this clause came from, why it's written the way it is, and kinds of detailed background. So this is good fun story time. I'm going to tell you a story that was told to me by the former head of the ISA 84 committee. When I joined the ISA 84 committee back in 1994 is when I joined the committee. I was only a couple years out of college, and I got put on the committee by Mr. Walt Bajak. But the leader of the ISA committee at the time was a gentleman, well-respected, well-loved gentleman, Vic Majoli. And Vic Majoli is the guy who's responsible for this clause. And it's all because of something that happened to him. So Vic Majoli used to work for DuPont in the Northeast, the Delaware area, and he demanded to have this clause because of something that happened to him. So now I'm giving you a 20-year-old reproduction of the story that Vic Majoli told to me as why this clause is required. It all started on a stormy, rainy Monday morning at the DuPont plant. And everyone's going into work that day. And one of the engineers that was going into work at the DuPont plant had a rough night the night before. And basically, He needed to go to the bathroom. So my plant engineer's going up to the bathroom and he's not feeling good, and he goes into the bathroom and he does his business. After this guy does his business, he flushes the toilet and the toilet's clogged. The water keeps coming, the toilet fills up, the toilet overflows. The toilet continues to overflow and overflow and overflow. The engineer doesn't know that the toilet's overflowing. He's already left. Now, the toilet's overflowed and the water is spilling everywhere. What does the water go? Well, the water is going to find the lowest point and continue to drain downwards. Now, the thing to know here is that this bathroom is on the second floor. So when the water collects and goes to the low point, it's going to drop down and start dripping down into the first floor. Well, guess what is on the first floor underneath the bathrooms on the second floor? The marshalling racks for the control room. So, yes, the water starts dripping down into the marshalling room, and it's dripping right on top of the cabinet for what? The safety PLC. Now, this story happened in the 1980s. And in the 1980s, we didn't have the same kind of PLCs that we have now. We had the original OG PLCs that had been just invented. The advanced diagnostics did not exist yet. The advanced circuitry, redundancy, fault tolerance, none of that existed yet. This is the first generation of the original PLCs. And this original first generation PLC is sitting there on a rack, and the overflowed toilet is starting to drip on top of the cabinet that contains this PLC. Eventually, that water finds a crack, a crevice in the cabinet, and it starts dripping on the backplane. It starts dripping on the PLC itself. And eventually, the water drips into the backplane and creates a short circuit. So, what happens when you short circuit an unsophisticated PLC? Basically, everything in the field is energized, and there's no way you can shut it off. So the water dripped everywhere, not just the safety PLC, but the control PLC. Now the plant's going out of control. Everything's going haywire on the plant. Alarms are going off everywhere, but the shutdown system isn't closing the shutdown valves because the safety PLC short-circuited and it's shunting power out in the field, forcing all these valves to be open when they need to be closed. So what? They've got no switches. They have no manual shutdown switch that is going to de-energize the power to the field. So all of the SIS engineers, the engineering team's going crazy. They're running into the marshalling rack. They're physically grabbing the wires and pulling them out of the wall, trying to de-energize the power out to the field. Eventually, they were able to pull enough wires, break enough circuit breakers and fuses to finally de-energize all the safety valves out in the field, and eventually got themselves to a safe state. But as you can imagine, for Mr. Vic Majoli, this was quite the stressful experience. So he demanded that for safety PLCs, just in case somebody flushes the toilet and it ends up causing a dangerous failure that prevents the the SIS from de-energizing the outputs in the field, I want the operators to have access to a manual push button to be able to do this. All right, so that's the history of where this came from. But honestly, the equipment that we're using today is a lot better than the 1980s vintage that this story, whether apocryphal or true, is based on. So now we need to do some serious thinking as to whether or not we actually need this equipment and how this equipment is installed. And as a matter of fact, as most of you know, I am on the IEC 61511 committee, and this clause is getting seriously watered down in the next version of the standard. In the next version of the standard, you're going to get a statement that is more akin to manual means can be provided if directed by the SRS. So it's not even setting up any kind of baseline. It's really, really watering things down. All right, so story time's over. Let's get back to work. Let's get back to business. There is a rational reason why you would want to implement manual shutdown. Sometimes the operator might want to put a SIS final element into its safe state manually before the shutdown system activates. They might want to have a shutdown switch to de-energize things if the shutdown system even if the shutdown system doesn't activate, there are reasons that you might want to do that. There are some standards out there, like if you look at some of the API, some of the NFPA standards, they require you to have manual shutdown switches that are going to be able to move final elements to the same state. But we don't want to just do a blanket statement across the board that you need to be able to de-energize everything downstream of the SIS logic solver, because in modern plants that are remote, that's going to be extremely expensive. So you don't have to implement manual means of shutdown. They're only required, even now, if the SRS doesn't specify anything. So my key first message to you on this topic is your SRS needs to specify what your requirements are for manual means. Don't ignore the topic. Write down what your expectations are. And honestly, no manual means is a valid option. There's a good and rational reasons that you might not want to have any manual means to activate your SIS filaments. So step number one, key item number one, always document your philosophy for how you're going to do manual shutdown, even if your philosophy is, I'm not going to supply any. That will be standards compliant. Basically, anything that you say is going to be standards compliant. Just make sure you go ahead and do it. Okay, so the original requirement of de-energizing outputs independent of the logic solver is based on the OG 1996 version of the ISA 84 standards. And that was written based on the story I just told you, which is based on PLCs that are much less reliable than they are today. So if you think about it, modern SIL3 rated logic solver, that story I told you would result in all kinds of diagnostics. It would result in the SIS logic solver de-energizing, the power going out to the field. So if you have redundant SIL3 rated sophisticated logic solvers, maybe they are so good, maybe their probability of failure is so low that you don't need independence from the logic solver. It's not the 80s anymore. We got much better tech. Okay. And then the other thing to think about is, do I actually need all of my final elements to have manual means of shutting them down? So consider this. I've got a list of 4 bullet points of things that you need to think about one at a time for every SIS final element to make the decision on whether a manual means is actually necessary. Number 1, is there an alternate BPCS way to accomplish the same task? So think about a fired heater. So the fuel gas going to a fired heater. If the shutoff valves connected to the SIS didn't shut, didn't go to a safe state, do you need to de-energize, or is it okay that you would just take the flow control valve or the pressure control valve that's supplying fuel gas to the fired heater, go to the basic process control system and put that BPCS valve in manual and set it to 0%? So a lot of times you have a BPCS valve in roughly or exactly the same services of as the SIS valve, and you can maybe shut that valve using manual means instead of doing a bunch of additional wiring for the SIS valve. Okay, question number 2. Is there any benefit in actually performing the activation manually? So the reasons that you would want to do a activation manually is, number 1, sometimes you're going to want the operator to be able to activate that valve even if the sensors haven't detected a hazardous condition yet. You want to give the operator the ability to do something preemptively. The other item is, well, the shutoff valve didn't work and the safety PLCs failed. So I'm just going to pull the power. Again, extremely low probability that most people are discounting these days. Third item, are there other standards that require you to have a manual shutoff, and maybe even a manual shutoff that's independent of the safety instrumented system? Sometimes there are. NFPA, API, look through them. If an API or an NFPA standard says you need a manual shutoff, you should supply one, and you should document and design it as part of the SIS process and document it in the safety requirement specification. The last thing to consider here is there even enough time to take a manual action? The archetype for not enough time is going to be the overspeed shutdown on a turbine. So if you lose your load and start to overspeed a turbine, it's probably going to self-destruct in less than 1 second. So if an operator has less than 1 second to press a shutdown button, do you think they're going to do it? Probably not. So if this button is intended to accomplish something that's not humanly possible, what's even the point of supplying the button? There probably isn't a point. So go through every final element and consider how you're going to do this, why you're going to do this, and write down yes or no. Am I going to supply a manual means of shutdown? And if you decide that you are going to supply a manual means of shutdown, explain exactly how it's going to be accomplished. Okay, so now what are my means for, or what are my options for accomplishing this manual means of shutdown? Well, one of the mechanisms is just to have a target on the DCS. So I'm going to press a button on the DCS, and that's going to cause my valve to go to the closed state. That's probably the least reliable of the mechanisms. It's the most common for sure. It's definitely not independent of the SIS logic solver. But if you just want the operator to be able to trigger something preemptively, it's probably not a bad choice. It is the least reliable because not only does the SIS logic solver need to be able to do its job, the BPCS logic solver and the operator interface computer all need to be able to work to make this happen. Now, most of the time they are working, but it's not up to the SIL 1 or SIL 2 level, shall we say. Another option that's very common is to direct wire a switch as an input to the safety PLC. Once again, this is not independent of the SIS logic solver. But if the SIS logic solver has a 1 in a trillion year probability of failure or a failure rate, risk is tolerable anyway. So this is a very common way to do this today. If you have a sophisticated SIL 3 rated SIS logic solver, because it's feasible to do. Now, when I say it's a direct wired SIS input, if you consider like the modern large petrochemical plants or the modern refinery, there are going to be push buttons in the control room that the operator has at their console, but they're not hardwired per se. They're hardwired from the push button to a remote IO card. So you go from the push button to the IO card, but then the IO card is going to communicate digitally, maybe even up to a mile or more, to the logic solver, which probably is sitting out in the field close to the process. So that's a very common way of implementing push buttons today. They are, or shut down manual means. But you have to know that they're not independent of the SIS logic solver, and you need to think about, if you're going to use that approach, how available is your SIS logic solver when you're doing this. Most of your SIL 3 rated safety PLCs, you're going to be good to go. But if you're using commercial off the shelf, safety configured SIL 1, maybe you might want to think about something a little bit more elaborate. The two things that you're seeing on the right-hand side of the screen that are now a little bit more available to you represent the couple of mechanisms that are available to actually manually disconnect power independent of the logic solver. So the first mechanism, which would have been of great use to Vic Majoli when the toilet overflowed, is a terminal switch. So basically, if you look at this figure up on the top, this is a typical distribution of power to the field. You have a power supply with a positive and negative terminal, and that one power supply is going to supply all the power to the field. So your positive is then going to hit, like one terminal, and then it's going to drop down to the next terminal and so on and so forth. It could drop, 50, 100 different IO points. So what we need to do is we need this switch here, and when you open that switch, you're going to disconnect power to everything in the field. Now, that mechanism of doing everything is cheap. It's easy. You could probably buy a knife switch to install on your terminal block for less than $1, less than $10 for sure. But this has got two key drawbacks. The first drawback is when you disconnect the power, it's not selective. You're disconnecting power to everything. So it is the most massive, uncontrolled, everything went to the safe state all at once, which is a really scary thing to do. If you've ever been in the field when all the power is disconnected from the SIS logic solver, flares are going off. Oh, it's happened to me. It's a crazy thing. So, kind of a last resort, it's a possibility. But it is an inelegant way of shutting things down. The other thing is that this switch has to be located close to where this power distribution is. And this distribution is generally going to be in the field. So your board operates. So if you're doing the traditional, the traditional modern approach of a centralized control room, and then your PLCs are in a remote instrument enclosure in the field, the board operator is going to not be able to flip this switch because they're a mile away. You're going to be reliant on a field operator to go into the remote instrument enclosure, locate this switch, and flip it. So it's a cheap approach from a money perspective, but it is independent of the logic solver. But you also need to think that it has a very broad scope, and you're going to need to train your field operator to be able to flip this switch. The other option is a little bit more elegant. It's the one down on the bottom. And although it's more elegant, it is super, super, super expensive. So this is one output channel coming out of the SIS. So normally you send your positive to the positive terminal on your solenoid, and then the negative terminal on your solenoid goes back to the negative on that output card. Easy peasy. But if you want to interrupt that, you're going to need to have a switch that is going to disconnect that power going to the final element out to the field. So what we would recommend if you have an infinite amount of money and you want to do this elegantly is a 2-position selector switch. So right now it's in the normal position. And then there's going to be another position, which is, let's just call that the shutdown position. In the shutdown position, which is going to be kind of the red lines, the top switch becomes open where you disconnect the power to the field. And then the bottom switch, you close those contacts. The reason for the dual set of contacts is that if you put the shutdown switch into the shutdown position, you're going to wire another set of contacts to an input card. So the input card knows that you disconnected power out to the field. And then that's an input to the PLC. It's an input to the program, so that the program knows that somebody disconnected power to the final element out in the field, and it can communicate that to the to the operator, and maybe even take some more shutdown actions to make this shutdown happen a little bit more elegantly. So there is a wide variety. I gave you 4 different choices for how you can actually do this manual thing. Now, what do I actually see? The most common item is this guy right here. Direct wiring to an SIS input. But not every final element gets its own switch. Only a select subset where we rationally went through all the outputs and said, yes, this one needs it. No, this one doesn't. No, this one doesn't. No, this one doesn't. Yes, this one does. So for a small subset of the final elements, I'm going to wire to the SIS logic solver that I need to activate that final element. And that's because the SIS final elements today, or I'm sorry, the SIS logic solvers today are just that sophisticated. They're that good. Their probability of failure is that low. But if you don't have the best SIS logic solver, you maybe got that automation direct thing that you bought for $99 net. If that's the case, maybe you might want to use this configuration down here, which is very sophisticated, very elegant. But then again, if you were cheap enough to buy that $99 PLC from PLC Direct, you're probably also going to want to be so cheap that you're just going to want to put a $1 knife switch in your terminal strip so that if everything's gone awry, if that toilet overflowed, you're going to send somebody into the marshaling room to flip that one switch and just go ahead and disconnect all the power that's going out to the field. Okay, so that's all the technical content. Let's go hit this manual design workflow.
Question, Ed.
Yes.
When is the testing of the switch carried out? During the commissioning stage or pre-commissioning stage?
Yes. It's even carried out during FAT. So if you have a switch that's shutting things, that's closing things out in the field, even during, if that signal is coming into the SIS logic solver, it's definitely going to need to be part of the FAT. Then, when you are doing your installation and commissioning, the switch, the shutdown switch, is going to be one of the loops that you're going to need to check off during that commissioning process. So when you're doing your commissioning, you're going to be checking to make sure that switch operates as designed. Then, when you're doing your final validation test, the pre-acceptance testing, the final validation test, the SAT, the SAT, you're going to want to do it then. The only question then lies is, do I need to test these switches during my periodic function tests? And the short answer is no, you don't have to, because manual shutdown switches are not part of the safety instrumented function. And because the manual shutdown switches are not part of the safety instrumented function, they're not part of the SIL verification calculation. Testing them is not required. So if you want to be complete and comprehensive, absolutely go ahead and test those manual shutdown switches, but you are not required to. That said, it's part of the design. So FT, commissioning, SAT, those switches should be part of the process. Is there another question, Chris?
There is. Are there any considerations that need to be accounted for with regards to the manual switch and spurious trips? What about dangerous failures?
Okay, so all manual shutdown switches should be designed and all of these configurations that I just gave to you here are what we refer to as non-interfering. So if you look at this knife switch, there is no mode of failure of this knife switch that will cause a dangerous failure. This bottom configuration, this two position or two channel select switch, there is no dangerous failure mode of this equipment. They can cause a spurious trip, but there's no way that these switches can cause a dangerous failure. So, absolutely unequivocally, there's no excuse to design a manual shutdown switch system that can generate a dangerous failure. You should always be able to do your design in a non-interfering configuration. Now, are these is this additional equipment capable of causing a spurious trip? Absolutely. What is the probability or what is the frequency of random hardware failures of switches? Vanishingly low. Switches just don't open up for no reason. There's a mechanical force that is required to move them from one state to the next. Them just for no reason falling open is a vanishingly low rate, something that I wouldn't even bother to consider in my spurious trip rate calculations. More questions, Chris?
Yep. Is
Okay.
there any standard requirement to have manual SD switches in both field and control room? For example, severe toxic gas release where the field operator is unable to reach the location.
Okay. I am not aware of any, but I don't know every standard for every process in every industry. So if you look at the functional safety standards that talk about design of safety instrumented systems, no, they do not go into that level of detail. And even the sector specific standards. So if you look at an NFPA 85 for boilers and NFPA 86 for furnaces and ovens, those standards have requirements for manual shutdown switches, but they, as far as I know, as far as I recall, don't require them to be both in the control room and in the field. But now, is there a standard that requires it? I can't tell you that there isn't, but I don't know of any. In my experience, I'm not aware of any that requires you to have field switches and control room switches.
Okay, does it have limitations of pipe size to set a manual shutdown valve?
Pipe size, manual shutdown valve. I'm not aware of any standard that sets the need for a manual shutdown switch based on the pipe size. The need for a manual shutdown switch is almost always based on what is the application. So an NFPA standard might require a manual shutdown switch on a fuel gas supply, but it will require that manual shutdown switch regardless of what the pipe size you have for the fuel gas is. So I'm not aware of any standards that will set manual shutdowns based on a pipe diameter. Now, something, you know, if there were one, it would be on pipelines. Uh, Whether it's a toxic material pipeline or a fuels pipeline, and those pipeline standards. Everything that I'm talking about now is based on the IEC 61511 standard. If you have a pipeline, you're also going to need to follow, well, let me step back a little bit and say that in the United States, so I'm only going to kind of speak to the rules in the United States. There are Department of Transportation DOT regulations that are going to tell you about the design requirements, including the spacing required for manual shutdown valves. Uh, those are additional requirements that are really outside of the scope of what I'm talking about right now, because right now I'm really focusing on the functional safety standards. Uh, those Department of Transportation standards may have some manual shutdown requirements that are going beyond what I'm talking about right now. So I would refer you back to DOT regulations. And if your questions are related to DOT stuff, send me an email when I get back to the office the week of March 3rd. So not next week, but the week after that, because I wasn't really thinking about pipeline regulations when I was doing this. I was specifically thinking about C61511. So the design workflow, step number one, what is your application? And does your application have industry specific standards that require manual means of shutdown? If they do, implement the manual shutdown and implement it in a way that is consistent with those standards. Bullet point number two, if you do all of your manual shutdowns exactly the same way, it's going to be most efficient to document that as a general requirement in your safety requirement specification, as opposed to putting that information on a final element by final element basis in your data sheets. Now, if you do have basically, if you do want to document it on the data sheet by data sheet basis, or you have exceptions to the general requirement, you will need to document them in the data sheet. So right here, you're seeing an Connexus Vertigo data sheet for preparing safety requirement specifications. This is a final element data sheet, and you'll see that you can expose a section that talks about the design of manual shutdowns, including tag numbers, whether or not they're required, and then details for how they should be specifically implemented. And then the last item says, if you don't implement manual shutdowns of your final elements in your safety instrumented system, you should consider providing a justification of why you didn't put the manual shutdowns in. You might have like one general requirement statement saying that I'm using a SIL3 rated logic solver, therefore the probability of failure is exceedingly low, therefore I don't want to have manual means that are independent of the logic solver. Or on a case-by-case basis, you might say, I'm not putting a manual means of closing this valve in because I have a basic process control valve in the same service, and we have written operating procedures to where that is the valve that should be shut in the case that the SIS valve were not able to move to its safe state. So that's our workflow for designing manual shutdown. So in summary, wrapping things up, in this webinar, we talked about the standards requirements for manual shutdowns, and the standards requirements were pretty brief. They said you need to document what you're doing for manual shutdowns, and you need to provide a manual shutdown for every final element that's independent of the SIS logic solver. Unless you don't want to do that, then write down what it is you want to do in the SIS or in the SRS, in the safety requirement specifications. We talked about considerations for when you might want to include a manual shutdown, and when you might not want to include a manual shutdown. So you will want to include one definitely if a other application specific standard says that you need it. And you might want to include it if one of the 4 reasons that you might not want to include it are not true. So basically, you probably should default to including a manual shutdown unless you can justify not putting it in. We explained 4 different options for how you could do those manual shutdowns. Something as easy as just a DCS target might be suitable for you. Manual shutdown switches that are wired to your SIS logic solver if you have a good one. Or you could do a very sophisticated one switch per final element that's actually de-energizing the power off the field. Or you could do the rough and ready, quick and dirty, just one terminal switch in the marshaling rack that's going to pull power to everything that's going out into the field. And finally, we talked about the manual shutdown design workflow. So what are the steps that you need to follow as you design and document in the SRS your manual shutdown philosophy and design for your safety instrumented system. So that is all I have for today. But before I wrap it up, I'm gonna take the rest of your questions. And I see, Chris, that we already have a question. Let me know what it is.
Yeah, we got a few of them here. How do you set the test interval for the valve in a manual shutdown of an SDV if there is no SIL requirement?
Chris, put on the calendar for a webinar, whatever the next open slot for a webinar is. I have a webinar that is how do I determine what the test interval is if it's not a safety instrumented function? So that I wrote a paper about this in, I think I wrote the paper in 2011 or 2012. It was a long time ago. Um, that basically says, well, I have alarms that need to be tested. I have manual shutdown valves that are only manually activated that need to be tested. What test interval should I use? And I've just made the decision that I want to turn this into a webinar as a whole. But the gist of that webinar is that when you have an alarm or a manual activation, they are part of a protection layer. So an alarm is part of a protection layer. Manually closing a valve is part of a protection layer. How much credit did your LOPA take for that protection layer? Probably 0.1. But you don't get to use that entire 0.1 PFD for that alarm or for that manual activation. If you go through the 61508 standard, you'll see that there are budgets. And there's usually a budget of 35% for your sensor, 15% for your logic solver, and 50% for your final element. So if your final element has a budget of 50% of 0.1, its probability of failure should probably be 0.05. So your test interval on that valve should be sufficient to generate a PFD of 0.05 or less just for the valve. So we're going to hit this topic again in a webinar coming up in the future. I assume that you've written that down, Chris. But that's my recommendation for test intervals for manually activated valves, because at the end of the day, they are part of an IPL. That IPL has a PFD target associated with it. Next question.
Okay. SIFs with pre-alarm, what is the assurance that operator will not take action during pre-alarm but can take action of manual shutdown?
If I have a function where I have a pre-alarm and the operator didn't do anything about it, and then my safety function activates, but the valve doesn't close, why do I think that the operator is now going to push a button and close that valve? Whew. Well, that's an interesting philosophical question, and I really don't have a good answer for you. Um, they're probably not. I mean, if they ignored the hazardous condition the first time, they're probably going to ignore the hazardous condition the second time. But the standard, there are other scenarios where the operator maybe didn't have enough time to respond to a pre-alarm, but they know that the SIS valve didn't activate because its limit switches didn't move. And now that they know that there's supposed to be a shutdown and it didn't happen, they would take action. So I understand the desire to have manual means of shutdown independent of the logic solver in some cases. Uh, but I mean, when you're looking at one scenario, if they had the opportunity to pre-alarm and they didn't, are they going to realize that the SIS didn't activate and take manual action? Probably not. Also, you have to realize that operators are very hesitant to act on pre-alarms, especially if they're afraid that they're going to lose their job if they take action on the pre-alarm. But if the shutdown system tried to shut down the plant and the valve didn't move, that's a different type of action. That's a different level of operator requirement that I really wouldn't discount it out of hand, and it's really dependent on what the situation is. So I guess I'll kind of summarize the answer by saying it's really dependent on what the situation is. The pre-alarm is the ability to respond to a pre-alarm and the ability and desire to respond to an alarm that indicates that the SIS didn't activate to take a manual action is just very situationally dependent, and you can't always tie them together. Next question, Chris.
All right, there's one in here. It's kind of lengthy. I'm not sure I totally understand it, but it says if you
Oh,
don't
give it a
want
shot.
one, if you don't want one, I'm not sure what that is. What are some valid justifications for not having one? I assume that means manual shutdown, maybe.
Okay. Oh
Okay,
yeah,
yeah,
yeah, yeah, yeah.
manual shutdown. I know you mentioned process safety, reaction time, but are there other ones? What type of supporting documentations or justification is required, and can you justify not having it for the entirety of the SIS at one time, or does it have to be done on a per SIF basis? Could you do it in the general requirements?
Okay. So the short answer is that one justification at the general requirements level is that this manual the purpose of the manual means is to be able to manually make a final element move when the SIS logic solver fails to move it. A real broad justification is that the dangerous failure rate of a SIL3 certified SIS logic solver is so low that there's no benefit in any manual means of shutdown. I don't know if I would do that if I owned the plant, but if somebody made that case to me, I could not disagree with it. You're basically backing up something that has essentially zero probability of failing. Okay, that's one thing. But on a final element by final element basis, there are means to say, I want to do it for this one, I don't want to do it for that one. And the ones that you don't want to do it for are the ones that have a really short process safety time where there's realistically no benefit. And then the other ones are, well, if the SIS valve didn't close, I've got another way to accomplish the same thing. Maybe I've got a BPCS valve in the same service. Maybe a shutdown system from another plant is going to close my feeds coming in. So there's no benefit in having that valve. So there may be other means to get yourself to a safe state than that one SIS final element, and then that manual shutdown switch provides no benefit at all. So there's, those are the key reasons that I could do it a different way. I don't have enough time, so it provides no value. And I could do it with another way in the BPCS or shut down of the plant. Other final elements kind of obviate the hazard and makes it unnecessary. There are a variety of means of doing it, but if I could roll back to the beginning of the question, putting in equipment to back up something that never fails, that is a justification in and of itself that can sit in the general requirements.